Awesome. So we're off for today. Um, Thanks for continuing with the course. I think these are the last two lectures, so we're also like fairly towards the end of it, and you can all reclaim your weekends after this, hopefully. Um, so logistics first, we have about 2 weeks until the final project presentation. So I'll shoot some updates on about that on campus via later today. But just to tell you, there will be a 6 to 7 minute presentation per team. It can be a 4, 5, 6 slide presentation. I would advise you to cap it at 6 or 8 slides, just so that you have enough time to spend on each slide. There will be a couple of judges. We'll have some folks from industry, some folks from academia, and so you'll get a balanced perspective on how relevant is this research. Could I write a paper about this? Um, what other directions can I take this in? And other general questions you might want to ask them, and they might want to ask you more importantly. So we'll have that. This week we'll be grading our midterms. Since there was a second round of midterms, we haven't released the grade for the first one yet. We're waiting on some students to take it this weekend. Um, I think that covers all of the logistics. So last two classes, project demo day after that. We'll also take a poll on whether demo day is more preferable during the week or on the weekend. I'm assuming it's okay on the weekend for now, but if that's an issue, please feel free to send me a message. We have so far covered linear models, deep neural networks, convolutional neural networks, and now this last part covers recurrent neural networks. And so we also saw advanced architectures in CNN. So we're also going to do some advanced architectures in RNNs the next time, which includes attention and transformers and all of these cool tricks that make RNNs work. But this time we're at least going to establish why sequence modeling is important, what sorts of models exist, and also talk about the challenges associated with training in a computational sense, because a lot of the work around RNN literature, and particularly RNNs, there were a lot of issues with training compared to other models. At least, again, this is not in a theoretical sense, but in a empirical sense, like that. That was what I came across, and there were all these blog posts about, tips and tricks for training your RNN that you won't necessarily see as much for other models. But that was due to this reason that there were some computational complexities associated with it. And typically, when you're modeling sequences, it's hard to parallelize. And so all of those things will come up during our lecture today. But I'll still try to keep it a short lecture. So you're back trying to get back from midterm and exam and lectures and stuff to, okay, we're back to learning. Cool. So let's get started. So I'm going to talk about this. Last week or the week before that, I was working on with a student on a project that dealt with GDP prediction. GDP is gross domestic produce. It is an economic indicator for a country. Let's just leave it at that. So we collected a bunch of data, economic indicator for the, I don't know if I should say prosperity or production of a country. I should probably say production. And so we collected a data from a bunch of World Bank and IMF websites, and she collected the data. And then there was some missing column. So she went back and manually found those data sets for these missing years and filled whatever was missing by hand. And the simple thing we started to do was, okay, there are some X's, which are the covariates. There are some Y's, which are, there is a Y, the GDP, which is the target. So let's just throw this data at a linear, let's just throw a linear model at this data. And we decided to start with linear regression. And this is somewhat, this is exactly what the data looks like. So we have the GDP for a bunch of years. We have the political rights in the country. We have the civil liberties in the country. We have the percentage of population using internet across these years. We have the consumer price index, which is in a sense a measure of the inflation. We have the population density. And finally, we have the gender equality indicator, and we have the consumer price index. I guess a different scale of it. I'm not sure about this last one actually. And so the bottom line is So the bottom line is there are some x's, there is a y. You want to predict y from x, so why not just use linear regression? And so we did that. Um, Turns out it's not that great. It's really not giving us the results we were sort of expecting. And I'm going to pause here. And at this point, you all have worked on all of these things. You understand these sort of assumptions involved and like what broke. So I'm going to try and ask you, okay, if a student texts you on WhatsApp saying, "Hey, this broke," and you don't know anything other than all of this information that I've given you, what are you going to say? Like, why do you think the results were not great? And this is a real problem. Just to tell you, this happened 2-3 weeks ago. So how would you deal with this? And to be clear, you can unmute because I don't think there are. I don't think people are going to clash. So feel free. Linear regression is high bias. Need more variance. Well, need more variables in x. Sorry, I didn't read the rest of the message. Okay. Need more variables in x. Okay, one of the things could be that we don't have enough training data, enough columns to predict the GDP. I will give you that. That could have been one of the reasons. But there's a much more powerful reason, or at least I think there is a much more clear reason why the linear regression didn't work really well. I'll give it some time. Think about what you do in linear regression. Think about what you're doing here. I'll go back to look at the data. Um, yeah, I didn't want to do that, but okay. Um, so these are your x's, these are your y's. I'm not sure if you saw the slide after. You probably did, but sure, you could say that there aren't enough x's to make an effective prediction of GDP. But I would argue on a high level there are some x's that are measures of we actually wanted to compare authoritarian and non-authoritarian countries, and anyway that's a separate part of this. But yeah, I guess you saw the slide. There is another reason though. Time matters is one of the reasons. I'm going to pause and ask you for another reason why you think why linear regression might not be yielding the results that we would expect, or at least results as good as what we would expect. So again, I'm going to
Is it
point
because
you.
collinearity among variables?
Is it because?
Is it because of collinearity among variables? Like we need to remove that because if variables are similar, we may not get the right output which we expect.
So correlation between columns, is that what you're saying?
Yeah, my bad. Yes.
I will give you that. There is correlation. So there is a specific term I'm going for. That you are on the right track. It's just the
Like we use
like
VIF to remove the like very similar variables.
this is fair. The slightly more accurate idea I was going for is, you see this column on the left? These are years, right? In linear regression, we don't typically have years, and I don't know if you thought about why that might be. Have you seen linear regression being applied on a data set with years on it? Open question. No. Can you think of a reason why we don't use linear regression where there are years? It has to do with what you just said. except slightly different. And to remind you of what you said correlation between columns. So Joseph says because that would imply time itself is the cause if you measure r square. Well, again, sort of what I was simply going for is now that we have time, all of these are ordered in time. Suddenly we have a case where order actually matters. Like if I switched around 2004 and 2005, that would not be the same pattern as if it was ordered by year, right? So all these rows of data are not independent. They are drawn from some distribution in a particular sequence, and that sequence matters. So we see that, for example, a percentage of population using internet is increasing across all the years. If I shuffle this around and I remove the column years, then suddenly the pattern in percentage using internet really changes. And you can't assume that these data points are independent because they're ordered by year. So basically the point was time matters, but also data is not independent. So regression, typically you assume there is IID data. And what does this mean? Well, you shuffle your training set, you shuffle your test set, you shuffle your validation sets. That is not possible with these kinds of models because now you have a time series. And in a time series, what you're trying to capture is, okay, so if this is the pattern before, what is the pattern after? So it's not simply a GDP prediction task, it's a GDP forecasting task, which is slightly different from this idea of regressions and predictions. Do people buy this? Mm-hmm. That's great. Cool. So the entire point of what Smola jumps into the math for was this idea that in a lot of cases in machine learning, you assume the data is IID, and then you shuffle and then batch it around and then learn from that data. But you assume that these data points are not correlated. And that is a problem because if the data is correlated, then that assumption is false. In a lot of cases in real life, the data might not be correlated, but a lot of other cases it might be. So that's what he says, that look, we are collecting X and Y observation pairs, and you assume that they're drawn from this distribution, joint distribution of P over X and Y. And what you're trying to do with your regression task is just estimating the conditional distribution of Y given X. And then you assume that there is this distribution. So what if there is a new X? What will my Y look like? That is your regression task, right? But now in this task, the order of the data did not matter. So things like images and objects, things like general regression problems, houses and house prices. The price of one house does not affect the price of another house. So somewhat like even in a real world situation, if you're doing that, you might want to think about which house was sold first. In some cases, some houses being sold at a premium indicates that the house prices in that area will rise, and other houses sold at a premium. So like if you really think about in the real world how this works, that actually might be the case. So again, there are correlations or there are hidden correlations in the data, but you assume that these don't matter. And typically things like, he basically talks about situations where you have an environment, you have an agent, or you have a set of actions you can take and the environment responds, and then you take a sequence of actions. So for example, um, in stock market data, for example, you want to predict I don't know, take stock market here, but I was going more for the active learning, reinforcement learning, and bandit stuff, where there is a clear environment. So in active learning, um, you want to select the next data point for which you think will improve the model the most. So that's how your training progresses. In bandits, you pick a particular option. So for example, if you're playing cards and you have a bunch of different steps, you think some steps will yield to a reward, you take those steps and then you get the reward and estimate that sort of thing. A similar sort of setup in reinforcement learning, where you take an action, your environment responds, This is like the typical setting of 2-player games or multiplayer games and so on and so forth. But generally, like these actions are not independent. Like an action reward pair is not an independent data sample. So that's all he's trying to drive home, that these systems have a particular state and you're modifying the state, and in different states you will have different responses. So you can pose with a rhino if the rhino is in a tranquilized state, but if it is not in a tranquilized state and you try to pose, your outcome is not going to be great. So just like for you already probably understand this, but it's a nice memorable example to have. And then there are things like just most environments don't seem to be stationary. Like your training data and your test data might not actually come from the same distribution. So it's, suppose you're learning a particular sine curve with some noise. Your test data is not necessarily going to be like that sine curve. It might actually be a straight line after, and then whatever you learned, even if you learned a really good model that fits your training data perfectly, you're not going to do well on your test data. So yeah, there is that. There is, we spoke a bit about covariate shift when we were doing batch norm. We spoke about label shift. Well, we actually didn't speak about label shift, but again, like you might just get unlucky. Like that is the bottom line, that shifts happen. All your assumptions are layered to make it a pretty problem to solve, but life is not pretty. So there is actually a chapter on heteroskedasticity that I would recommend if you want to learn a bit more about this in the Shalizi stats series that I shared. That was very cool. Like we studied, like there is this simple assumption that all of your noise is IID Gaussian. And if that is not the case, then what can you do to solve this stuff? So there are things that people do, and that is an entire area of statistics that people research where, you know, there are these long tails, there is high variance noise, there is like basically stuff messing with your predictions and what to do if that happens. But we well, at least I wasn't taught that in school, so never thought about that as much. There was another cool example that he gave, which is from the Netflix challenge. So Netflix had $1 million data challenge, and someone just plotted the average of the ratings over time. And if you can see, about before whatever time period for the first 1500 days, it was roughly around 3.4, and then suddenly there is a shift, and like the average rating hovers around 3.6, 3.7. And he asked the question, like, why do you think this is? Do you think suddenly ratings recommendation systems just got better? So they got better at showing you movies that you would rate higher. It doesn't seem to be the case. Like that Netflix didn't deploy something massively new at that point that changed everything. What they simply did was they changed their rating system, in the sense, if they had said before the rating 1 corresponded to I hate this, I don't like this movie, and later the rating 1 corresponded to I hate this movie. So people started thinking like, okay, I definitely don't like this movie, so I'm going to rate it 1 before. But then afterwards they started saying, well, I don't hate this movie, it was okay, so I'm going to rate it about a 2. And so that implied this average shift in rating upwards, but not because of the recommendation system, just because of some arbitrary label changes. And a similar sort of spike, that there were these spikes in the movies you rated. You rated like movies older as a bit, I should be more clear about this. So the movie age in days versus your mean score for the movie, you tended to rate newer movies better. No, you tended to rate older movies better. This is confusing. Right. So you tended to rate movies in a sense where, so okay, so with older movies, what happens was you and I are typically not going to go and look at movies from 20 years ago unless they were really, really good movies. So it tended to be like a selection bias where, okay, for if I'm going to choose an older movie, I'm probably going to want to watch that movie because I saw someone else review it and it was a really good movie, because I didn't really know about that movie until I read about a good review somewhere. So that's the sort of selection bias that happens with older movies, and newer movies. You're likely to watch them without getting a lot of feedback, and you're going to be like, it was okay. But with older movies, that definitely won't be the case. Cool. So that's a selection bias example. And again, the overarching theme is like data is non-stationary. There will be shifts, there will be random things happening, there will be correlations. And so this assumption that, oh, all my columns will by default be uncorrelated, that is not true. All my data points will be uncorrelated, that is often not true. So just be sure to check how badly you're doing if those assumptions are broken before jumping into data sets. And comes up with another cool example where there is this spike when the movie wins an award, and there is an influx of people saying, oh, it's a good movie, it's a great movie. Then after a bit of time, people forget that it won an award and they're like, nah, it wasn't that great. But anyway, that's the general idea. He gave an interesting example of a similar kind of thing, like the satisfaction, life satisfaction for a sample of German women in terms of years before and after marriage. So evidently, life satisfaction increases till the point where you get married, and then again starts going down. So it's just again indicative of like life giving you an award, which is marriage, and then your rating for life increases, and then again after a while you forget that, oh, marriage was a big deal, and then your rating for life goes back to what it used to be. But anyway, that's I think that's the general case with a lot of us. And again, also another example where the increase in money does not necessarily mean increase in satisfaction. And this one particularly, like that, there are a lot of things to be said about this. So I'm not making any absolute statements, but it's very interesting. Like Daniel Kahneman, I read a couple of his papers just out of interest. He's also written a book called Thinking Fast and Slow with someone else, and he is a Nobel Prize winner, if I'm not mistaken, some prize winner. Anyway, cool papers, cool effects, cool books. You should read about these things. But bottom line being, data varies for random reasons. For example, the west coast of the US is prone to earthquakes, which is fair, which is known. But like, why are there earthquakes in the middle of America? And turns out that earthquakes are not due to the same factors like tectonic shifts and stuff as the other earthquakes, but rather here, in this case, it's due to fracking. Like there are artificial disturbances created that create tectonic disturbances that create earthquakes. So again, like your data is not just non-stationary in time, but also in space, and it might be due to arbitrary reasons. So when you're making modeling assumptions, think about these things. This is Oklahoma fracking. You already, I mean, at least a bunch of you have been working on time series prediction, so you know this better than me, but clearly time series are correlated. There are certain reasons due to which stock prices fluctuate. For example, the dot-com bust, the dot-com boom, and then the dot-com bust caused stock prices to fluctuate. There was a subprime mortgage crisis. I don't know if anyone knows about the 2008 financial crisis. It was basically people sold a bunch of bad loans, and one day people realized, oh crap, these are bad loans, and then there was a sell-off. I'm oversimplifying, but there are cool movies about this. At least one of them is called The Big Short. I use that movie to understand what this crisis is all about. But back to sequence modeling. Too long don't read. Data usually isn't IID. That was the entire point of all of these things. And with that established, let's jump into sequence modeling. So we have said that there are, and at this point I should start annotating. Cool. So there is a certain joint distribution. Before we said this was just a bunch of the x's. So I mean, it's actually already written, but okay. And any joint distribution in general without making assumptions can be factorized as p of x. Well, I should have started with a simpler example and then shown you this as a, let's use eraser. So if you buy this, then you will, I mean, given a joint distribution, you can always write this as p of x2 condition on x1 times marginal distribution of x1. Is this fair? Do people buy this, or does anyone have an issue with this? Okay, I'm going to assume you buy it. Just post in the chat if you have issues. I'm also going to say this is the same as, yes, it is true as part of the definition of conditional probability. Exactly. X1 given X2 times P of X2. I'm going to say these are equal. Do you buy this? Yep, it can be derived from conditional probability in either direction. Absolutely right. But now the problem is if I want to model this, what do I do? Like this is like the chicken and the egg problem. If X1 is the chicken and X2 is the egg, then this one says that the egg came after the chicken, or sort of like egg condition on chicken. So there was a chicken before the egg. But the other one says, well, but also uh, chicken condition on the egg. So the chicken came after the egg. So which is the correct one to model? And there I will pause here. Can someone answer this? Like, can you tell me which one is the correct model for a joint probability if I have a chicken and an egg? My opinion, probability of chicken given egg. Okay. Any other opinions? Okay. Seeing none, I am going to buy that you are confused. I'm going to assume that you are confused, and you should be. It is unclear, like without additional data, just given a chicken and given an egg, you don't know which came first. And it is the same with a lot of data where that is why we make this IID assumption, because we don't know which point came first in a lot of cases where we just have a bunch of data. But with the stock market data, with this series of actions and rewards, the point is that it is a series. We have them ordered in time. So what we can do is we can say that, look, this data point came first, this data point came after. So if there is an arrow that points from one to another, it has to point from the one that came first to the one that came after, or the ones that came after in any case. So that time ordering gives us the solution to this chicken and egg problem. If I know that I had a chicken at time t0 and I had an egg at time t1, then it is likely, it might have a zero probability, but it is likely that the chicken created the egg. So if I had to draw an arrow, if you put a gun to my head and said, give me a good model, I would draw an arrow from the chicken to the egg because I know the chicken was there first. And so with a lot of time series data, the nice thing to have is like time, because now we know that we want to condition xt on the ones before it and not the other way around. Well, this is the wrong conditioning. I'm just labeling the nodes for you to see. But yeah, let me clear that out. So this is the right conditioning direction because we know time. That's about it. Like that is all there is to sequence modeling. To begin with, like what are sequences? How do we model them? Why this particular factorization of x on everything that came before it? And to reiterate in the general sense, this p of x is equal to p of x1, x2, dot dot xt, and we're saying it factorizes as p of xt on everything that came before it times p of everything that came before it. Sorry, yeah. Let me just write this down. That's easier. So this is again just in case you didn't follow. This is equal to p of xt on x1 to t minus 1 times p of x1 to t minus 1. I'm abusing indices, but hopefully this is clear. And then you factorize this further as p of x t minus 1 conditioned on x1 to t minus 2 times p of x1 to t minus 2. And hopefully this makes sense to you. And so you keep factorizing until you arrive at this each, like a factor for each corresponding to each node in this graph. Cool. Moving on. So someone came up with this idea that, hey, why not just use like a function of the previously unseen data? And they called it an autoregressive model. And the challenge that the first challenge that you might see is there is a lot you have to condition on for each of these factors. And so one of the things that you can do is, well, yes, you use a function, but that function still has a lot of arguments that you have to model, a lot of data, a lot of, again, the general problem is a lot of computation. If there wasn't a lot of computation, we'd be good. But there is. So even for autoregressive models, you need to make some simplifying assumptions. Like, sure, every point is conditioned on a function of all the points before it, but maybe the simplest thing to do. Sorry, there's a question. We are turning an unsupervised learning problem into a self-supervised learning problem. I'm not too sure about that. We are, for now, like all we are doing is modeling.
Like,
Yeah, go ahead.
so like if we see in this case, so like if you say like this particular unsupervised learning problem, so like we don't have any target label as such, like let's say given some data, right? But if we say in like general language modeling or sequence to sequence task, so now what we are doing is we are conditioning it in some way, like basically having this temporal dependence. So like we are converting a unsupervised problem into a self-supervised, which is conditioned on like the previous data that occurs, right? In some sense.
So this is a great comment because maybe I should clarify what I'm trying to say. So we said that p of x, y, which is this supervised learning problem where I have a particular y, p of xy is equal to p of y given x times p of x, right? This is the conditional distribution, and this is what we want to learn. This is how we make predictions of y dash given some new x dash, that kind of thing. Um, uh, cool. And right now, I'm just talking about this part. Like, I don't know if there are labels or not or whatever. I am just talking about how I wanted to factorize this p of x. Is this fair?
Yeah, I think yeah. I think my particular yeah makes more sense for language modeling where we generate some word like so we don't have any target label sort of purpose like it's unsupervised task and we are converting into a self-supervised. But yeah, this is more of like here we have some data, let's say
You're
time series
absolutely
data.
right. But if I say something about the p of y given x, like y's might be derived or y's I might already have or I might not have the like true ground truth, and I might generate some labels or whatever, like that, whatever the problem framing has to do with p of y given x. But right now, I'm just talking about the model,
Yeah, yeah. I think yeah, I
right?
got it.
So yeah. So it's the same as saying I can use a linear regression for predicting real values, predicting classes, or whatever else for forecasting. It might do very poorly, but it can do that. Um, but I'm just talking about like how I think my data was generated, and that is separate from what loss function I use, how I frame my errors, and what sort of problem it is. Hopefully that's now clear, but thank you very much for raising that. That was very important to bring up. So all we're doing is talking about the model. And so the simple thing to do is like, okay, instead of all the arrows that we had before, this point affecting all the points that come after, let's truncate it. Let's say that, okay, I want a window of 3 points. I won't look at dependencies beyond that. So yep. So a window of 3 points in the sense this one arrow, this two arrow, like I should say a window of 2 previous points before it. So in this case, tau, the value of tau is, could someone tell me? Xt is conditioned on 2 points before it. So the value of tau should be two, exactly. So, and this is again an assumption we are making just because we don't want to condition on everything before it. So you can condition on everything before it if you have infinite computation and you want, you know how to, we'll see some errors that happen because of that. And it's some very simple math, like we'll get into the vanishing gradient problem and the exploding gradient problem, just in terms of like one operation that causes it. But again, I'm getting ahead of myself. Right now, we're just talking about limiting the modeling, like limiting the model complexity by making some assumption that, okay, condition on 2 points before it, we should be fine. If there is any doubt, pause me. Please feel free to do that. Sounds good. So yeah, so this is called the Markov assumption, where we actually say that condition on 1 point before it, it is independent of the rest. So what am I going to say? The Markov assumption states that x t is independent, independent of x1, x2, all the way up to xt minus 2, condition on xt minus 1. So in this case, we are limiting the window even further. We are saying limit the window to 1 and condition on that 1 point before it, it is independent of all the points that came before. That's all that's a Markov, that's called the Markov assumption. And the massive advantage of that is now we do, for each point, we don't have to condition on all of its predecessors. We just have to condition on 1 point that came before it. And the natural question you should be asking is, well, is that really like feasible? Is that like fair to do? And of course it is not. It is completely arbitrary, and it might not even be true for a lot of cases, but for computational purposes we have to do that. Otherwise you're going to really blow up all of, like, by conditioning on all the values of all the variables coming before it. And so there has to be a better way to do this. And with that, people came up with this plan B, which they said was, okay, let's just replace all of these dependencies with this green node. And let's say that this hidden state is updated at each time step by all the points before it. But now, instead of taking all of the x's before it, you put each x into a hidden state, and then you take the hidden state into the next hidden state. If that, in a very hand wavy sense and visual way, makes sense to you. So instead of all this x going to each other x, this x now goes to, should erase this, yeah. So instead of this x going to every other x, this x now goes to one hidden state, which is propagated forward and in a sense reaches every other x. And that is exactly how, like, we frame this problem of recurrence, and then we use neural networks to learn these recurrent sequences. So if I had to make a prediction at each point, then I would say, okay, I've learned a hidden state, and now I'm going to make a prediction for some output at each time step from this hidden state, because this hidden state captures everything that comes before it. If there are questions, this would be a good time to start with clarifying questions. If there are not, then let's look at this math for this hidden state. Okay, so what we've said was we want to factorize this x as something conditioned on everything that comes before it. Oops. does the hidden state need an initial condition? Yes, there is an initialization because there is an h naught that doesn't have anything coming before it. So if this is my x0, this is my h0, that goes to x0. So this will be initialized by whatever choice of initialization scheme you decide to pick. Yeah, I assume that's what you were asking. If that was not, then please clarify. Yeah. So yeah, all of these tiny details are important, but at least maybe I wasn't a good student and I wasn't paying attention when I was taught, but yeah, that's important to mention. So great questions. Thank you for clarifying. Oh, and this should also go here. Cool. So this is now we have like, okay, this is our latent variable model. The reason this is latent is because we don't really know what this hidden state is, but we do know what the x's are, right? So we have our inputs. We don't know what hidden state it will learn. Like we don't have the observed data for the hidden state, but we want to model it such that it goes to a hidden state. So we create some function that takes x0 and that takes h0 into creating this h1. So that's all this is saying, that ht is conditioned on the two elements before it, ht minus 1 and xt minus 1, where t is an index for time. And then xt, so this x has two arrows coming in. So x given x0 and h1. So ht and xt minus 1. And so that is basically describing what our model is doing. So it's important to understand this language of graphical models, because that is super useful in conveying information very succinctly. Cool. Let's move on. So the reason, so a physical example of a latent state is when I ask you, did you understand this? Because what is observable is the words I am saying and the sound I am making. But what is not observable is how much of that relates to increasing your knowledge. Knowledge is not measurable. Tests are measurable. Questions and answers are measurable outputs, but knowledge inherently is not measurable. So knowledge is like the latent state that produces this output of words and answers if I ask you a question, right? That hopefully was a better clarifying example of what this h and what this x indicates. And so we're saying with each word that is spoken to you, you update the hidden state, which is your understanding. Wow, that's bad handwriting, but okay. And that understanding then impacts the words you might answer back in response to a question I might ask. Yeah, so hopefully that's a good clarifying example of what this h and this x implies. And this generally is like latent variable models are super popular, and is generally a good way. Like people don't use plan A as much as people use plan B, latent variable modeling. And the added advantage is now that we have this h, it still captures everything that comes before it. But now we don't have to have a function of everything calculated at each time step because we already have h. Cool. Start moving a bit faster. And so in practice, like all of these observable data sets that we have of clicks, of purchases, of likes, of use, of app use, emails, all of this, that is the X, and there is some U, some H, which is the hidden state, or which is some intention the user has that these companies really want to capture. Like if they can capture our intentions, that is really big, because intentions don't change as much. Behavior might the output might be very sparse, but intention, if you can capture, you are good to go. And that's what all of this stuff that, the Cambridge Analytica stuff that happened, part of it was like we are capturing the psychology of users, and that's probably how they sold it to lawmakers. I don't know how true it was, but that was why lawmakers were very like into it. They're like, oh, cool, we know the psychology of our audience and we can exploit that. Should don't know if I should have recorded that, but okay. This is my opinion. This is not my employer does not endorse this opinion. This was a hypothetical company called Cambridge Analytica that had nothing to do with any real company named Cambridge Analytica. Please don't sue me. Cool. With all those disclaimers, there are different ways that latent states that you can infer these latent states given some observed data. That is a method called statistical inference that 10 years ago, if you were doing research, at least that's what Smolla says, then all you would be doing, or at least if all you would be doing was this building these forward models of behavior and like inferring what these hidden states were, that was cutting edge machine learning research or cutting edge statistics research. Today, though, that isn't the case because now we just throw deep learning at it. But before, what we used to do was build these custom algorithms that can infer. In this case, he's using Y as the hidden state, but yeah. Yeah, anyway, the takeaway is just like build complex forward models, perform this inverse question of what is my hidden state if this is the observed data. That was a big deal 10 years ago. Today, that is not really the case. Again, I'm going to skip over this because it's not as crucial to get into right now. I don't want to confuse you folks. Oops. Oh, okay, I can't clear my screen. Sorry about this. Okay, cleared. Nice. Let's go for. Yeah, an important question you should ask is, this is a parametric model because it is a model which I have given some parameters to and given some structure to, and I'm trying to learn what the values of these parameters are. Are these parametric models really true? No, they are not. They are almost certainly wrong because they are. We have layered assumptions on top of assumptions. We have said that we assume that this hidden state is learnable given like it is a function of all the previous inputs. It might not be. We don't know if it is or not. We don't know if it is learnable from the data or not, but we know that this is a fair assumption like we can make compared to all the other ones that we have made. Yeah, we have two initializations, HX and CX. How is CX conditional inputs? I don't know what CX you referred to.
I think is going back to like LSTMs. They have like cell state probably.
So okay, so I haven't gotten to that yet, and I probably won't get into this lecture. So maybe we can discuss this in the office hours after people have had a chance to review like at least what we've done in this lecture. That is an important question. I mentioned HX, at least like the initialization for H naught could again be a choice of like what you like. Like Xavier initialization is one way of going about it. Random initialization is another way. By random, I mean random normal. And again, that relates to tips and tricks for training recurrent neural networks. There is no logical initialization that you should have for a hidden state. Like there is no theory, at least to my knowledge, there is no theory as to what initialization you should pick. But there is empirical evidence that some initializations work better than others. Probably doesn't answer your question, but hopefully gives you enough information to find an answer. Cool. So getting into the Markov assumption first. Really quickly, there's not too much to this. We only say that there is a window placed, and beyond this window, we limit our assumptions like previous to the 2 time steps that we've seen. Beyond this, we just truncate the gradients. So we don't take gradients beyond this at all. We just say there is no dependence, remove it. It's not great, but it dramatically reduces computation. And it does work in some cases where the dependence is not particularly strong. So it's because the Markov assumption is really popular. cool. We're not going to get into the demo, but let's jump into the applications of these things now. So you have a better grasp over this plan A and plan B. What is this Markov assumption? What is this latent variable model? So we have spoken about we actually haven't spoken about words before. If I remember, yeah, I've never spoken about words, but we've spoken about this idea in naive Bayes where we used to take the estimate as the count. So if there is an estimate of how frequently does the word stock market investing appear in spam emails, that estimate, instead of like a probability distribution, you can just count the number of times it appears in the data set that you have and make the assumption that this is a fair sample, or like just an unbiased estimator of the sample mean. Again, what I'm going for is just like if someone asks you for a distribution of spam words in spam email, just count them, and that's the best you can do. Unless you have more knowledge, you can do that. Anyway, that's all of this math is talking about estimating it as just counting it. That is what this n refers to, right? So if you want to model tokens which are like for a sentence statistics is fun, and you want to count that there are some passages that you have, and you want to estimate the probability of the word is following the word statistics. And I say this following because again, this is in time, right? So you look at language as a series of words generated one after the other. This after is in a time sense. So you now have this, you now have these nodes, but this nodes corresponds to is, this nodes corresponds to statistics, and there is a dependency. And you just want to estimate P of stats, comma is equal to P of is given stats times P of stats. And so you say that, well, I don't have the true distribution of this, but I have the count of this. So I can count how many times is appears after stats and how many times stats appears by its marginal distribution of stats. So I use estimates of these probability distributions, but this is important as a mathematical concept to understand that this is just an estimate. It's not a distribution. It's just what you have in your sample. There can be many samples of data from the same true distribution. Hopefully this is clear because this is important in general. And then this becomes n, and that's why this becomes p hat, because it is an estimate. It is not the exact value. Another question, whenever you have the chance, does the hidden state happen to obey any properties like a Markov chain being stationary? I don't think so, but I feel like those are slightly different concepts, like the Markov assumption and the stationarity of a Markov chain. At least in my head, I don't know offhand the relationship. Yeah, I'll have to get back to you on that. Stationarity though is like my obvious the answer that is coming to my head is no. I just want to be sure that yeah, so that convergence to some value, it depends on the stationarity of the time series that you're learning. Yeah, that's a much better framing. Thank you. So the question is, I guess a better way to frame it, does the hidden state converge to some value? Yes, and so I would reframe that as, do we want it to converge to a value? Like, do you want your past knowledge to converge to a certain value and affect your current knowledge? I would say no, because you want your hidden state to be updated, because as you're seeing new data, you want that data to affect the hidden state in some sense. And yes, in like a long-term sense, you want it to start forgetting very old knowledge and focus only on new knowledge. But again, that is a sort of an update step. So subject to application, I think it would be Yes or no, but that's not a great answer. Hopefully I give you some intuition, but yeah, I will clarify that. Okay, cool, awesome. So yeah, getting back to using tokens and words as tokens. The domain is countably finite, sort of skipped over that. But so when we get to converting words into data, you use encodings. Like you can't work with strings for machine learning. You want your strings to be represented as numbers, because then you can do matrix multiplication on numbers, but not strings. So the simple way to do is, oh, every word, give it a new number. And I have this mapping stored. So in the end, I can map back whatever numbers I get to the words I had. Yes, this is plausible. You can do this, but then every single word in the English language will be mapped to a number, assuming we're working in English. So that is a problem. And you know that some words are common. Like you don't want to map the word cat and cats to like very like mapping these to 0 and 1 gives you no information. But really, like these two words are pretty similar, right? So you're losing that similarity information by doing like a single number per token. So you want to do something smarter, and that is all of like language modeling has gone from like here, like this. We did start here, to be clear. Like language modeling was here at some point, but then they got to doing smarter things, like maybe encode cat as 0 and then cat plus s as something else, 0 plus something, whatever. But this plus epsilon, or some where epsilon is some value. But anyway, the point being, you maintain some sort of similarity even in the mapping, so that you can say that cats minus s is equal to cat, that sort of thing. So 0 plus epsilon minus epsilon is equal to 0. So this preserves this relationship. This does not preserve the relationship. And the entire point of machine learning is to preserve patterns in the embeddings that we have. So that's where we started going. I need to clear my screen again. Clear all times. We are good to go. Okay, so some slightly smarter ideas were n-grams. So n-grams are similar to like, I want a 3-letter sequence to capture where n is equal to 3. Maybe you want 4-letter sequences, maybe you want 5-letter sequences, whatever. You choose your n-gram model. I don't feel like right now we want to get into the maths, because I haven't actually. I want to. Well, it's basically what you're just saying is like condition the rest of the word on the n-gram that comes before it. So, and again, like we've discussed before, the distribution can be estimated by the count. So how many times does cats occur if you see the sequence cat before it? How many times does s occur? I should say s and cat is equal to s times cat. And I should write p of all of these, but okay, hopefully it's. And all of these are now estimates because we don't have the true distributions. Anyway, this is hopefully now clear. And what do I want to say? I don't think. I think this is about. Yeah, I think it is about adding some sort of. So again, if there are no, so here, I guess all they're saying is if I feel like we've covered this. That's why I'm hesitating to cover it again. It's just like if there is a count of 0, then you don't want 0 in the denominator. You want some sort of smoothing. Because if a word has not occurred, that doesn't mean it's not a plausible word. That just means your data set does not have it. So you don't want that to create a problem later on saying, oh, this is an impossible word. no, you still want some sense of this is a feasible word, I just haven't seen it yet, so I want to still model this. And that's what this epsilon is about, that don't keep the count of, even if the count is equal to 0, add some value as some constant here, which is in this case epsilon. Again, not super crucial, like the key idea was this thing, and then the rest of the math follows. Cool. Moving on to this is a demo, so let's go back to an example, like a visual example of this. So suppose I have this sentence and I want to tokenize this sentence. Key idea was just mapping this text into sequence of IDs. We discussed that there are different ways to take IDs. You can take n grams or like series of tokens. You can take each word independently. You can take each character independently. So each character independently will at least result in like just a small vocabulary. So A1, B2, C3, and then Z26. But then what you need to do is like you are expecting your, like I said, you're ignoring like the dependencies between the word cat. You're going to say this is C, this is A, this is T, and so you will have to learn that some tokens appearing together, like 3, 1, 19, 20, no 19. 3, 1, 19 are like a meaningful word, whereas Cas is not a meaningful word, and you're expecting your model to learn this by itself just based on the data that you have. So you're going to need a lot of data and a lot of compute if you want to do that, or you could be a little smarter and start doing word encoding. And we discussed word encoding, and then we discussed considering frequent subsequences and encoding those instead. And this seems to be like the Goldilocks zone, or like the good fit. I think that's all I'm going to say, because we have an example following right after. So you want to generate your mini batches of like, here is my 4-letter sequences. Oh, right. There is a space. So there's a 5-letter sequence. So space is encoded, right? Good catch. So yeah, so these are 5-character sequences. And you want to generate your mini batch from your data. There are, again, different strategies for this. You can randomly partition your mini batch, which will give you sort of independent samples. But the challenge then also is that you will have to, so these are random sequences, like these, I don't know what to say. Randomly sequencing your words or randomly breaking off parts of your sentence are going to give you independent samples-ish. So within the sequence, the characters are still dependent, but roughly outside of the sequence, the characters are like independent sequences are possible. There is a question. Is the epsilon used to deal with unseen data during testing? You are absolutely right. So in the test, you might see cats, but in the training, you might not see cats. So if you just use count of cats, then you're going to train for 0 cat, and you're going to see a cat in the test. So yeah, you want to deal with this, like cat is a plausible word, so add that epsilon in the denominator during training, so that you're not surprised by seeing some data occur in test. Cool. So we have random partitioning that gives you independent-ish samples. Yeah, I don't think I want to say anything more about that. I need to reset the hidden state. I guess. And now, instead of random samples, if you actually do sequential partitioning, so you keep the sequence of the data, slightly better, I would say, just because, again, like now there is a relationship between each sequence, so you can learn a hidden state sequentially and expect it to capture some of the pattern. Again, so this was just how a more concrete example instead of the coding example of how to segment your data and what sort of segmenting you want to implement. So you can randomly segment, you can sequentially segment. Length of the sequence is again up to you. How to determine that? Well, empirically, what works is what works. So yeah, that's all of these choices are why like training a good RNN is not as straightforward. I guess you could make an argument that your choice of kernels and all of that stuff in CNNs was also arbitrary, so you have to try out a lot of stuff to understand. But yeah, either way. So far we've spoken about just sequences and learning on sequences. Now let's get into like plan B, which was latent variable models or RNNs, where we now have a hidden state that we think is some latent variable, and we have the observed actions or the observed inputs about from the data. Cool. So if you want to make a sequential prediction, then at each, and you have a new hidden state H, you have a new X. The way you make a prediction is you say this hidden state captures everything before it, and I'm going to make a prediction of the output. That's how you make a set of predictions. And so after X, you can you have a new hidden state given a new X in the sequence. Given a new X in the sequence, you have a new hidden state, and you can make a prediction. That's how I should draw it. Yes. But either way, you follow the sequence of actions now. So mathematically, all this is saying is that there is an during the learning process, the hidden state is a function of the weights of the hidden state times the hidden state before it. So if you take an arbitrary hidden state in the middle, then this weight WHH. So when did I become so bad at writing? WHH, then you have WHX, and then there is a bias that is added, just plus B, right? That bias is a fixed constant that you learn. So that's about it. Like this complicated math is just saying the hidden state before it, the X before it, multiply by matrix and add it up. That's fairly straightforward. And the output, if you want to make a prediction, is just a function of this bias of the output. So B output, I should say this is BH, that means. So this is WHO times HT. Yeah. And that gives you the output at whatever stage you are at. So observation update, hidden state update, you're now familiar with all of these notations. We have gone through the math. Let's jump into autoregressive models. So we said autoregressive models are these models that just summarize a hidden state as a function of all of the inputs before it, right? But well, we said that this H really captures all of the inputs before it. So instead of saying all of this, let's just say H and the xt minus 1. The assumption we are making here is that this latent state does actually summarize all the relevant information about the past. We don't, and I'll get into like why this is an assumption and what happens when it fails. But so far, this is what we have said, and that gave us this HT given these two elements, XT given these two elements. Cool. Now, again, we've been over this, so I won't jump into this as much. Let's go into language modeling with recurrent neural networks. I'm still waiting for when, I guess after this we get into a discussion of when it fails. So we spoke about first doing a simple encoding of characters. So the simplest way you can do something is that you create word vectors which are just a one hot encoding. So there are some characters. This says that there is a T. This says that there is an H. This says that there is an E. Again, for the T, we replicate the same array. For an E, we replicate the same array. So the dumb thing to do is like, okay, we have a one hot encoding of each character, but now like there is an embedding matrix, and this is something that will be learned, which when multiplied by these vectors, by this matrix of word vectors v, gives us a meaningful output representation. How do we constrain these outputs? How do we? So the question then is, what is this matrix? Well, you can learn this W by forcing words like cat and cats to be close together. So you're saying that when multiplied by W, this vector, well, v and v dash should be close together, and that sort of thing. So the goal is to like improve your embeddings to actually make generate meaningful word representations. I shouldn't have used v and v dash because they used v and v dash. Okay. Yeah. So again, we reiterate the same sort of mechanics, except now we speak about like how this goes about. So we read the sequence to generate hidden states. Then we start generating outputs. Outputs will actually be used as input for the next hidden state, and therefore the next output. And that's how we claim that this hidden state captures everything. Again, I'm still sticking with we claim because we haven't validated what these hidden states are doing. But like we're just going through the mechanics of how RNNs work, right? And then finally, for an output vector, we have another decoding matrix, W dash, which gives us our original word representations that we had with our zeros and ones. And so this will tell you what word. Oops, sorry. Yeah, I think this is it. Oh, oops, this is the other way around. So this should really be this. That this should be our decoding matrix W dash or encoding. And then this is your decoded word vector. Yeah, I think he wrote it like this. Then he drew it like this. I'm just matching the colors to what we saw before. So these are the canonical word vectors. Cool. So again, we learn this W by forcing it to learn representations of words that are close to each other to be decoded to the same words. Oh, there's a question in chat. Sorry about that. We use some form of, is the epsilon used to be? We don't see. Okay, it's the same question. Okay. Sounds good. Okay, now we get to like, okay, how do we take the gradients and how do we actually like the real, like the key things about recurrent neural networks that are really what people spend a lot of time trying to understand. So the first thing you have to realize is, yes, there is a very long chain of dependencies. All of this x1 to xt minus 1. Actually, how are we doing on time? I think we're doing okay on time. Okay, we should be done in the next 20 minutes.
Sorry, just one more point to add about word embeddings. So the point, this is the main idea or the goal of word embeddings. We use like this particular weight matrix W is to convert like this discrete data into a continuous representation. So now like since we have like this continuous representation, we can run like backpropagation and all like do optimization things. Otherwise, if we have this discrete data, it is a bit difficult compared to like that way. So like this is why we convert like this particular discrete representation into continuous representation and like then perform it through a neural network and like perform the backpropagation as it is.
This is absolutely, this is an excellent point. Yeah. So you want your words to be embedded in a space that is continuous, where if you sample from points next to each other, there will be words that mean similar things. So you want cat and cats to be further away from music and rhythm, for example. So yeah, that's a great point. Cool. But what we're talking about was gradients, and we said that there are a lot of things that an hidden state depends on. So that means when you take the gradient of the hidden state, it has to be back propagated to all of these things. And this is a sequence. So you start at the end for the gradients, and then you back propagate until the very beginning. That's very expensive. And more than that, that will create problems because at some point it might actually be a very weak relationship and the gradient might disappear. And then you can't do anything before that. You're like, well, what do I do now? So again, like I'll get into this. This is very important because these are the two main problems of recurrent neural networks: vanishing gradient and exploding gradient. And it is extremely simple as to why that happens. But like the simple thing to do is clip your gradients to prevent them from diverging. Um, yeah. And so he mentions this butterfly effect, which is important. The butterfly effect was something like, it's like all these time machine these time travel TV shows will tell you that something that happened years ago, a very minor thing, can affect something very major years later. So if you go back in time and probably take out Hitler, then it's not necessary that the world will be better later, because that might create some other ripple effect and change time. But anyway, the same thing in terms of data dependency, like data a long time ago could have affected data later in some weird way. And so you have to go back and keep track of all those dependencies, and that's why backpropagation is hard and complicated. The score, the sort of perplexity, is what you measure as how well your model. It's a measure of accuracy. Typically, okay. You typically measure accuracy with log likelihoods, but the problem with log likelihoods as an accuracy metric is that you can't compare different lengths of data. So in an intuitive sense, what you're saying is, I am going to give Jay 7 tests and sum up his errors across all those tests. And I'm going to give Joseph 1 test and just use that as the error. And that's not an equal metric. Like Jay will probably not score 100 on all those tests, whereas Joe might also not score 100, but only on 1 test. So he'll lose out like 5 or 10 marks, but Jay will lose out 5 or 10 marks across all of these tests. And if I just sum it up, then that's not a fair metric. So I have to sort of normalize this on like a length of the sequence basis, so number of tests basis. So that's what this is saying, that if you have a sequence of different lengths want to be made comparable, then just normalize by the length of the sequence. And so that creates this that gives us an exponentiated version of the accuracy metric that we want, which is effectively the number of possible choices on average of words that you're going to predict. Hopefully that was like a clarifying example of like why perplexity is a better metric than just negative log likelihood. Like typically you use negative log likelihood in a lot of places, so it should be made clear about why this is. Now we get to the cool parts. So backpropagation, truncated backprop through time. By truncated, what you mean is simply this. Simply this. Ignore the math. Just look at the diagram. Think about like, oh, I should change color. If you are backpropagating these gradients, then at some point you're just going to stop. You're going to say, beyond this point, I'm not going to backpropagate. So I'll just remove those gradients out after like a point, and it's called detaching gradients. And this is a choice. Again, this is an assumption you have made, saying that dependency does not go further. But it turns out to work like decently, or at least initially these were like the decent approaches that actually worked. But like I jumped 5 slides, so let's now go back to like the math and like how this evolved. I just wanted to show you like what is truncated gradients and what does it mean. So we started here. Clear this. So we started here. We said the hidden state is a function of the previous hidden state, the previous input, and some weights, right? And the output is a function of this hidden state and some weights. Now, I'm saying this because I'm going to use these things. So the loss function, okay, it's easier to change slides, right? Yeah, that's great. So the loss function is over the input, the output, and the weights, right? The input, output, and weights are basically it's a loss of target minus prediction, and the prediction is basically this thing, right? Before this we said prediction is G of H and W. So this is G of H and W. I am dropping the time indices for slight less visual pollution. And now we want to take the gradient with respect to the weights of this loss. So sum over T gradient loss with respect to G. I didn't drop the time, but anyway. And so this reduces to this. And note that the gradients are here with respect to the weights, here with respect to the hidden state, and here again with respect to the weights. So again, if you write this down, you should be able to expand it out fairly in a fairly straightforward manner. But this is basically all you're doing. So you're saying I will take the gradient of the loss with respect to the output, and I will take the gradient of the output with respect gradient. Put with respect to the weights, and then this is expanding it out. Sounds good. Yeah, if there are questions, ask me and I will be happy to walk you through it. But I just wanted to give you that intuition that this is not complicated math. It is just a substitution from the previous slide. And now you come up, oops, clearing screen. Complexity is the exponentiation of cross entropy. I need to clear out slides, and I have about 15 minutes to wrap up. This is great. Okay. So the objective function that we come up with is a certain loss. We already expanded that out into what we saw on the previous slide. The problem that comes about is this last term in the loss is now it's like a recursive gradient. So the gradient ht depends on all the h's that come before it, right? Ht minus 1, which in turn depends on ht minus 2, up to h0, right? So when you're taking gradients and you're using the chain rule, you have to back propagate each point back to the beginning. So that's when like people realized, well, what if we don't? Like, what if we just stop here? What if we don't back propagate beyond 2? Well, that is when you create a window of 2 hidden states that affect the third one. So ht minus 1, ht minus 2. That's how this idea of truncated gradients came about in a mathematical sense, where they said, well, this term is going to be really painful to evaluate. Well, what if we just don't? There was no there's no like reasoning, like there is no more complicated reasoning behind this. They just decided not to. So yeah, that's what they decided, and that's what they did. But like, yeah, this is the expansion of what happens if you keep trying to back propagate, and there is this function. This function is one of the inputs, the hidden states and the weights, and you want to take the gradient with respect to the hidden state before it. Yeah, clear all of this. And so these were the problems that they ran into, where there is a color. There is a stability issue. It is very expensive. You have to go back too many terms. So yeah. Yeah, this is just the same explanation that you have to, clear screen. This is the same explanation that you have to go back all the way, but instead you just stop here. Cool. So we have been through the math and also intuitively understood why this whole thing, why someone came up with this. And this is exactly how a lot of machine learning works. Like someone just decides to do something and it works. They're like, maybe I don't do this complicated calculation. Maybe I find a substitution for it. Maybe I just like arbitrary reasons and they work. So yeah. So another idea that, and I'm just going to mention this, it's not like super important for you to understand this because it doesn't actually work better in practice. But another idea that someone came up with, like how research works, was they said we'll use a random variable called epsilon, and we will make this epsilon an expectation 0 random variable. So in expectation, it doesn't really affect the output. But with a certain probability, epsilon will go to 0. So you're basically truncating the f of x t. Basically, you're truncating the gradients. This is a gradient term, right? This delta gradient with respect to hidden state is being truncated, but in a random way. So on average, you are still getting unbiased gradients because this expectation is 0, but you are not choosing like a fixed time to truncate to. You are changing that about on the basis of the value of this epsilon. So it's like a Bernoulli random variable with a certain probability p. I guess p upon 1 minus p, because you wanted to go to expectations. Whew. This is a great graph. Like if you ever want to refer to what is going on in a recurrent neural network, this is the computational graph. So you have an input, you start here. You have an input, you start before that. You select a random state h naught. You select a weight matrix. You initialize those things. You multiply your first input with your first hidden state with the weight matrices and add it up and create this first hidden state. Then you use this hidden, if you want to predict an output at this stage, then you go and multiply this by the original learned, original unlearned output weight matrix, and you predict the first output. And then this is for now. This is how you forward propagate all of these things. And then when it comes to back propagation, you calculate the loss. Like you compare your y1 to your o1. You say that there is a certain loss between these two, and you propagate it back to the learned weight, now the learned weight matrix, and propagate all of these back. And then there's a second layer. So h1 goes to x2 and h2, and again all of these. So yeah, this is a great computational graph if you want to sit and look it through. But we're not going to do that. We're going to get into exactly why this gradient is problematic. And this will be the end of the lecture. I don't want to push you far beyond 10:15 today. It's cool. So we have seen these matrices hx, hh, and oh. And this corresponds respectively to the output, the hidden state, which depends on the x before it and the h before it. So x before it and the h before it. How did that happen? Okay. X before it and the h before it. Yeah, I don't think I want to say anything more about that. So we have this, we know this, we know we want to take the gradient, we know that it is equal to a complicated product. We know that we also have to ultimately end up with the gradient of the hidden states, gradient with respect to x. Like this is all the same things as we said before, except like in a different format. Like instead of the pi, we wrote product, and we summarized everything nicely. But yeah, that is where we started off. And we have a simple recurrent neural network. So the same diagram that we've seen before. Now the problem arises in a mathematical sense, because with this full recursion, if we don't truncate gradients, then basically the gradient of the hidden layer at t with respect to the weights of previous hidden layers is a product of, I should probably not start there. Probably start at gradient of ht, ht plus 1 with respect to ht is equal to this weight matrix. Do people buy this? This one sentence. Let me clear all this. I'm just talking about this one sentence. Is this clear to people? Like if you take the gradient of one hidden state with respect to the one before it, the only thing that affects this is the matrix that multiplies one hidden state into another. Because that x part is currently not under consideration, that is constant. So with respect to the weight matrix, that is not unaffected. So because, oh nice, they've written it before. So if I take gradient with respect to WHH, sorry, HT minus 1, then this goes to 0, and this basically returns HH. Do people buy this? Yes, should have started there. So that means that this is true. And this now, if you extend it beyond, like if you take products of all weight, like you have the chain rule, right? So you differentiate one hidden state with respect to the one before it, that with respect to the one before it, that with respect to the one before it. And that's how you basically propagate your gradients back. Now the problem that arises is every time this gives you a WHH, 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 assuming it is the same weight matrix for simplicity. But that gives you a product of weight matrices which is equal to the layers, that the difference in layers. So basically this T minus T. If I have layer T and I'm back propagating up to layer T, these many products of weight matrices because of the chain rule. Do people buy this? And yes, okay. Now that means that we have to examine what is this product really, or what is this product really. This is just a general form of the same thing. The general form, so if you have a matrix, and we discussed this very briefly, but any matrix, if you say, if you have a vector x, I should say vector u, just to have a different name and not confuse you. U is equal to x I cap plus y j cap. This is how you decompose a vector into its components, right? So we discussed that you can decompose a matrix into its components, which is called eigen decomposition. So in the same sense, so I won't talk about matrices, I'll talk about vectors to keep it even simpler. What happens if you take u square and x is large? Let's say 100x I cap plus y j cap. It basically grows exponentially in the x direction. Yes? Well, I shouldn't say it does grow exponentially even the y direction. It just x becomes really massive compared to y. Is this fair? Do you buy this? I'm going to assume you buy it. It's fairly straightforward. The point I'm going for is if y was really, really small and you take this 200 times, then what you're going to end up with is a really massive x and a really tiny y. And that is okay because this is like, at least u has some value. But if in the other case, like if this was 0.1 x cap and 0.1 j cap and you take u raised to 200, u is basically going to go to 0. Do you buy this? Yeah. And the exact same thing happens in matrices. So matrices have some things called eigenvalues. And the problem arises that when you raise this matrix to 200, if your eigenvalues are high, then this is going to blow up, which is what you call your exploding gradient. And if your eigenvalue is really low, then this is going to go to 0, which is what you call your vanishing gradient. All of this is because of this product of the same matrix over and over again. So when you say you have a well-behaved matrix, you mean that your eigenvalues can neither be too high nor be too low. So, and those it's very hard to constrain your weight matrix to those values. So yeah, you can always clip up and clip down, and people do this, by which you mean like a set of fixed upper bound and fixed lower bound, but then like you're in a sense constraining learning. So you don't know if you will run good representations by clipping, and you have to really try out what value do you want to clip it to, and so on and so forth. But it is as simple as this, like this matrix product raised to 200 will either blow up or go to 0 if the values are not conditioned well. And that was really cool. Like till date, I had never completely understood vanishing and exploding gradients as well as this slide explained it. So that was about it. So again, truncation in practice is just like this, calling this detach statement. Not the rest of the slides, not that important, but I will stop here, seeing as we are at 10:15. I will, of course, I'm around for questions for another 15 minutes, but I will at least stop recording. But this is like, so just to summarize, like today we've covered like sequences, the assumptions we make when modeling sequences, recurrent neural networks, what are the problems associated with recurrent neural networks, and exactly mathematically tied down why this gradient blows up or gradient vanishes.